Hi, my name is Ulrich ter Blanche. I'm a research engineer at the Center for Renewable and Sustainable Energy Studies, and today we're going to talk about wind energy. This slide is for the eThekwini Municipal Energy Office. We will start with an overview and brief history of wind power, followed by a discussion on wind as a resource. We will then do some basic wind power calculations, discuss the available technologies, and briefly discuss the project development process. Lastly, we will go through some frequently asked questions. Wind power. Humans have harnessed the power of the wind for centuries. It was especially used for propulsion by sailing boats. Later on, it was used in windmills to grind grain. More sophisticated systems such as Heron's wind power organ also existed in its time. In the 20th century, windmills became wind turbines for generating electricity. It started with a direct current turbine in 1887 by Scottish academic James Blyth, which this device was used for charging a battery. Later on, it progressed to alternating current turbines connected to the electricity grid. In comparison to internal combustion engines, wind turbines were uneconomical at that time. Diesel engines and steam turbines took over electricity production. Although during times of fuel scarcity, such as the First World War, Second World War, and the 1973 oil crisis, wind power flourished again. Since the 90s, the wind energy industry grew at 20% per year. Wind turbine technology advanced throughout the 1900s, with the most significant advancement coming from the Jetser turbine. It was a major breakthrough in the development of wind turbines. This was the world's largest turbine. It operated from 1957 to 1967 without maintenance, demonstrating incredible durability. The design served not only as a basis for developments in Denmark, but was adopted by wind turbine manufacturers around the world. We refer to it as the Danish design. With a blade span of 24 meters, it produced 200 kilowatts of alternating current fed directly into the electricity grid. Its electromechanical yawing, asynchronous generator, and the 3 stall-regulated blades with emergency aerodynamic tip brakes is a design that is still widely used today. The first turbine to change the Danish concept was the Enercon E40, which had variable speed, pitch control, used a direct drive, and had AC, DC, and then AC conversion. The wind power industry has experienced continuous growth, with the global annual installed wind capacity increasing each year, with exception to 2013. It reached a total installed capacity of over 422 gigawatt globally, and is expected to grow even more. In South Africa, most large-scale wind energy projects are installed through the Renewable Energy Independent Power Producer Procurement Program, in short, the REAP. The program is conducted through bidding windows, each window having an allocated installation capacity. Window 1 saw the installation of 634 megawatt of wind power capacity. Window 2, 562 megawatt. Window 3, 787 megawatt, and Window 4, 676 megawatt. It is worth noting that the electricity price for each bid window is significantly less than the previous window, starting from R1.15 per kilowatt hour, going down to 62 cents per kilowatt hour, a trend which is expected to continue into the future. By the end of Window 4, South Africa will have more than 3.5 gigawatt of wind energy capacity installed. The majority of these installations can be found in the Western and Eastern Cape, seen as blue spots on this map made by the Energy Blog. There are multiple reasons for these installation locations. Some of the considerations to include accessibility, wind resources, and proximity to existing infrastructure, such as high voltage power lines and substations. Now let us discuss resources. The majority how wind is created. Wind is the movement of air caused by differences in pressure. Air moves from a high pressure to a low pressure. system. Various forces in the atmosphere can lead to the creation of wind. On a large scale, wind is created by the balance between solar-driven pressure gradients, Coriolis forces, and friction forces, among other. In essence, wind power comes from solar power. The sun heats the surface of the earth and in turn heats up the air. Hot air rises, creating a low-pressure area. Cooler, heavier air from another area creates a high-pressure area. The high pressure naturally moves towards the low pressure. This movement of air is called wind. The Earth is constantly spinning at a high speed in a counterclockwise direction. Due to the Earth having a rounded shape, the distance from the surface to the rotating axis is further at the equator than at the poles. The speed at the surface of the Earth reduces from equator towards the poles, a phenomenon that can be experienced by moving from the edge of a spinning roundabout towards the center. If an object travels in a straight line, it will seem to curve as it moves away from the center. This phenomenon is known as the Coriolis effect. As mentioned in the previous slides, an air parcel initially at rest will move from high pressure to low pressure through what we call the pressure gradient force. However, as that air parcel begins to move, it is deflected by the Coriolis forces. To the right in the northern hemisphere and to the left in the southern hemisphere when viewed from the equator. As the wind gains speed, the deflection increases until the Coriolis force equals the pressure gradient force. At this point, the wind will be blowing parallel to isobars, creating a spinning motion. If we look at low and high pressure systems, we can see this mechanism at work. In this example, the wind would, without friction effects, be moving counterclockwise around the center of the low pressure system in the northern hemisphere. However, the wind slows down near the Earth's surface due to its friction, and therefore the Coriolis force weakens and the pressure gradient force becomes dominant, resulting in the spiraling of air into the center of a low pressure system and away from the center of the high pressure system. This causes convergence in the center of the low pressure system at the surface. It is this surface convergence which leads to rising air that can create clouds and even cause rain and storms to form. These mechanisms create weather patterns and the associated wind patterns. However, there are also various local factors that can influence the strength and direction of the wind at the surface, such as the landscape and the temperature. In order to identify a suitable location for installing wind turbines, you have to characterize the available resources. Power extracted from the wind can vary depending on the wind speed, wind direction, seasonal variation, among other. Various indicators are used to determine the suitability of a site for wind power, a commonly used one being the mean wind speed. Here you see an example of a mean wind speed map, made as part of the Wind Atlas for South Africa project, also known as WASA. The WASA project enables planning of large-scale wind power projects in South Africa. The first phase is seen in this image. A second phase is being implemented, which will include more parts of South Africa. It is important to note that a mean wind speed map is merely used for visualization in order to identify potential high wind resource areas. It is not used for site selection. Now let us look at wind power. The power obtained from the wind can be calculated. The fundamental units used in these calculations are obtained from the international system and also known as SI units. Power is the amount of energy used in a second, measured in watts. Power is commonly also used to rate electrical equipment in terms of their maximum capacity, such as for a power plant. Energy is measured in joule. However, electrical energy is commonly converted to kilowatt hours, which is the energy used per second